Hello, and welcome to this presentation, What do you mean by cache-friendly? I'm Björn Fahller. I live in Stockholm. I work for Net Insight. We make networking equipment. During this presentation, if you want to leave your cams on, that is okay, but please mute your microphone. This presentation, in many ways, can be said to have its roots a few years ago. Or many years ago, depending on how you see it. We were in the late stages of developing a new media switch. It's a beefy machine, bigger FPGAs, more FPGAs, bigger CPUs, faster CPUs, more of them. And in this late stage, I was doing some performance stress measurements if we were sort of in the neighborhood of where we wanted to be. And the results were extremely disappointing. They were really bad. So I started to try to figure out where is the execution time going? Why so poor performance? And I fairly soon found out that the main node controller CPU was pegged at 100%, which didn't really make a heck of a lot of sense, because in this kind of scenario where we were changing the network topology and adding and removing video streams continuously, the node controller CPU is busy reacting to changes, meaning that it's passing messages basically and waiting for responses. So it should be limited by latency and not by CPU. So that was weird. And then I found that on this CPU, it was one control daemon specifically that was pegged, and that is the one that is responsible for specifically for message passing. This was so weird, I couldn't understand it. So then I ran a profiling on it to see what's happening, and what I could see was that 75% of all CPU time was spent in one function, the function schedule timer. I was like, what? How is this possible? This makes absolutely no sense. So I looked into the code. It looked like this. It's an old C API. I have slightly C++ified it for this presentation. And by the way, what I'm talking about today is not a C++ topic at all. It relates to any programming language where you have some level of control over the layout of your data structures. Anyway, we see a start timer that has a deadline and a callback function, some user data, and a prev and next pointer. So it's a linked list. And then we have this schedule timer function where 75% of all CPU cycles went. So we can see that when we want to add a new timer, it traverses the list from the back towards the end to find the insertion point, and then it adds it. And then there is also a cancel timer, which is important because most timers actually are canceled. You set a cancel, you send a message, and you want to know if you get a response, which you typically do, or if it times out. So when you get a response, you cancel the timer because it's not needed anymore. And I'm guessing that most of you probably understand what the problem is here, why this was so slow. So this presentation, what do you mean by cache-friendly? Presentation that I wish that I had attended all those many years ago. The person who wrote that timer happened to be me. Now, in defense of younger me, when I wrote that, the system was much simpler, much smaller. There were a handful of timers flying at any time, and almost all timers were set equally far into the future. So adding a new timer was almost always just appending to the end, which meant you didn't have to search anything. But now in this stress test where I found that 75% of all the CPU cycles went into its scheduled timer, in this stress test situation, I was hovering at around 20 to 25,000 live timers at any time. And this is problematic. So let's have a look. What I'm going to talk about today is how to write code about the effects having a cache without knowing the specific details of the cache. So if you were hoping to learn how to squeeze every last cycle out of a known architecture, sorry, this is not that talk. So what I'm going to talk about is usually referred to as cache-oblivious data structure or cache-oblivious algorithms. I strongly dislike that term because it's not at all about being oblivious to having a cache. It's about it being oblivious to the details of its cache. To write reasonably performant software without knowing the exact details, I use this simplistic model view of how the cache works, how the memory works. This is a simplification, but I think it's a one. So we see the main memory, all your RAM. It's huge. And in the middle, we see a cache. One specific thing to note about the cache is that it's small. In this case, it's ridiculously small. There are 4 entries in it. No cache in the world is that small. We can also see that both the main memory and the cache are divided into chunks of equal size. These are called cache lines. And all reads and writes to main memory go via the cache and always in full cache lines, as they are called. And you can see that they are aligned. In this case, I have chosen 16 bytes of alignment because it just makes the slide easy. In practice, the de facto standard today is 64 bytes large cache lines. And then to the left, we have a little bit of source code where we can see what happens when we execute it. So, for example, here, if I want to read from the pointer named hot, we see that hot is 4004 hex. And if we look into the cache, we can see that 4004 hex is actually a hit, so it's there. So this is a blazingly fast access. Just get it right away, almost no time. But then we want to read from the pointer cold. Cold is 4048 hex. Cache, we see that 4048 is not to read. So what happens then is that the CPU chooses some line in cache that it decides that we can sacrifice it. Because to read something into the cache, something must go out. So in this case, it's through 0. And it's now evicted from the cache. And now we can read from the main memory into the cache. And this is a slow operation. It's like 100 times slower than reading directly from the cache itself. But now that the data is in the cache, we can do the read, and all is fine. And then we want to write to this other pointer, also called 4080 hex. 4080 is not in the cache either, so it has to evict something to be able to modify this memory at 4080. So it chooses a cache line, in this case 4010. And this white block here means that this cache line is dirty. We have written something to it that has not yet been reflected into the main memory. So what it has to do then is first to write this into the main memory. This is a slow operation. Now that the memory, the changes have been stored, we can evict this cache line, choose the one we want to get, and read it. And now we can finally do our modification. And then we want to make another modification to just the next address higher. But now it is in cache, so we just do the write. Now this cache line is dirty, and at some point in the future, we cannot really know when, it's going to be written to the main memory. So this is a mental model I have of how the cache works. It's a simplification. All models are wrong, including this one. But some models are useful, and I think this one is useful. So it includes some important aspects. For example, that the cache is small. We don't know how small, but it is small. And it consists of fixed size lines. I mentioned that the de facto standard today seems to be 64 bytes. And data access that is a cache hit is really fast. That is for free. Whereas a cache miss is slow. The CPU can do theoretically a lot of work, could do a lot of work while waiting for a read from the main memory. But it excludes a few things. It's a simplification, it's a model. It doesn't take care of the fact that in the real world you usually have a hierarchy of caches, several levels. You usually have a very small and very fast level 1 cache that is local to each CPU core if you have a multi-core CPU, which you typically do. And it doesn't take into account associativity. What means with cache associativity is that any given address in memory can only map to a few of the entries in the cache. It usually cannot map to all of the entries, which means that for certain access patterns, you can run into a problem where it seems like as if you were sort of wasting the entire cache, but in essence, you just have competition for a few entries in the cache for all your accesses. And I'm not going there, not in this presentation. And I actually think someone else should do that one because I'm not knowledgeable enough, to be honest. And I'm not talking about threading. Threading makes things really difficult because when you have a multi-core CPU and one thread running on one core makes a write to the level 1 cache on that CPU core, and then another thread running on another CPU, the other core wants to read that, then that cache is not updated with the changed update. So you have cache coherency protocols to ensure that the caches appear to be in sync, and that takes time. So the only advice I'm going to do about threading is keep it to an absolute minimum, the communication between threads. Do this as little as you can get away with. You cannot reduce it totally, but reduce it as much as you possibly can. You will gain performance from that. So that is my mental model of the cache. So let's now go into analyzing this timer structure. So what I've written here is a program that is just intended to expose the cache behavior of the timer. I really don't want to call this a benchmark because running a real benchmark it requires a heck of a lot more sophistication. But this one is just doing a lot of accesses so we can see where we have cache misses and cache hits. So I have a tight loop. I'm scheduling a timer with some random timeout time and do nothing callback. At least for the compilers I have, this is sufficiently advanced that they cannot understand that I'm actually not doing anything, which is important. That is one thing that is difficult when doing performance analysis. Compilers are too clever for you. And then every second revolution through the loop, cancel the timer from the previous revolution, just to be a little bit with how I'm exercising the data structure, which means that when you pass through this entire loop 20,000 times, there will be 10,000 entries remaining, and then we just fire all the callbacks. And doing so, we just, if the list is empty, then we return false. Otherwise, we call one callback, cancel that event, and return true. So the loop can continue until the list is empty. So one tool I like using for this, sometimes like, sometimes don't like, is Valgrind. Most people know Valgrind as a tool for finding memory problems, memory access use after free and memory leaks and such stuff. But Valgrind has a tool called Valgrind, which is a CPU emulator that keeps track of where your execution is. So it's essentially a kind of profiler. For every instruction it runs, it notices how much time is spent, how you got there, how the hierarchy looks. It's not cycle accurate, but it gives you a good idea. But here's the thing. Then we add a cache simulator to it. It also has a simplified cache. It doesn't try to model the host CPU cache. But you get, by default, you get a level 1 cache that looks like your level 1 cache, and then a last level cache that is big and slower. A cool thing is, though, is that you can actually give it parameters to change how you want the cache to look if it's important for you to do measurements on a cache architecture that is different from the one on your host machine. And then we tell it to dump instructions, because by default it saves information about source code lines. And as it turns out, this is usually not quite enough to understand what is happening. Sometimes it is, but often it isn't. So I'm sorry, there will be some reading of x86-64 assembly here. And then we add branch sim, because it's often important to understand sort of what is happening with the branch predictor. I will get to why later in this presentation. The downside of this is that it's incredibly slow. A slowdown of 20 times is absolutely nothing unusual at all. It can be worse. So that is a to think about. But a good thing also is that since it is a simulator, it simulates in isolation. It is the result it presents is unaffected by what else you're doing in the system. So let's go and run this one. So this, and you may perhaps notice that I'm using -01 and debug information. But this is a difficult one. It's a compromise. I have found that in my experience, and this may be that I'm just lucky, I don't know. I found that 01 optimizes enough to get relevant data access patterns, unlike 00, which gets crazy results. And it's still low enough level of optimization that it's fairly easy to follow the code and understand what is happening when you look at the assembly, which can be important. So let's run this one through Valgrind. Now, as I mentioned, this is an emulator and it's super slow. So what's happening is when you run this, it's for every instruction that you run, it remembers every memory access. Did it hit the level 1 cache? Did it miss? Did it hit the last level cache? Did it miss? Where in the call chain is it, so that you can see how you got there? Because in any normal program, you can of course get to a hotspot through different paths through the code, and it may just be one of them that is important. And this takes time, and it is intensive. And if this was live and you were sitting in the front bench, you would hear how my laptop is now howling like a jet engine, because it's working really, really hard. But I hope we will get a result soon now. See. I swear this one goes slower when I'm presenting and when I'm preparing. Maybe I should look at the Slack and see if there are questions. No? By the way, do use the Slack for it, if there is anything. So we can see a partial result already. So 2.5 billion instructions, 1 billion roughly data accesses, 700 million level 1 misses. So nearly 70% cache misses. That is impressively bad. It's difficult to write code that is that bad. But here comes the real thing. There is a tool in this is as far as I think it's Linux specific. I'm not entirely sure. Cache-grind is a visualizer for these results. It's amazing. So what you can see, for example, is a call graph. How did we get to places that are hotspots? In this case, the program is so simple that it's obvious what it is. But in a slightly more advanced program, this really helps a lot. And we can look at various different things, like where do we have branch prediction misses and such like with last level data read misses. But the one that is interesting now in this case is where do we have level 1 misses? And sum is just that it sums both read misses and write misses. So what can we see? Okay, schedule timer. 2/3 in this loop and in the condition, and 1/3 in getting the previous element. Okay, that is interesting. We can look at the machine code. Okay, so 2/3 when we compare a value we have in register with something we read, and an unsigned comparison if it's after or equal. Okay, so this is a is after function to check if we have reached the insertion point or not. And then 1/3 when getting the prev pointer. Okay, so we have some information. So let's see if we can understand what this means. We have our timer struct, and we have 4 bytes for the deadline, and then we have padding 4 bytes because the next entry pointer must be aligned on 8 bytes, and then we have the user pointer and the other pointers 8 bytes each. So we have a total of 40 bytes. So why did we get 2/3 of our cache misses looking at the deadline? Well, the thing is, we get to this timer by following a pointer. And if we assume that this entry is not in hot cache, then we must wait for this timer entry to be read from RAM into the cache so that we can look at the deadline and see if we want to go on. So there is one rule of thumb to begin with. If you're traversing a data structure by following pointers, assume that following a pointer is a cache miss, because it's really difficult for the CPU to predict where that pointer is going to point to. So it's almost always a cache miss, unless you have very specific information to the contrary. And then we have 1/3 for the prev pointer. And why is that? Well, if we look at this data structure, we see that prev is an offset of 32 from the start of the timer, and the cache lines are 64 bytes each. So if we assume a random-ish alignment of a timer somewhere, it starts somewhere in the cache line, it's roughly 50% chance that the prev pointer is on the same cache line and that is not. Which leads to the next rule of thumb, that data that is accessed together should be stored together. So that if you access one and maybe have a cache miss on that one, then accessing the next one will be a cache hit because you're not another cache miss, because you have already taken the penalty for the read. So chasing pointers is expensive. So can we do something that gets rid of the pointers? So one thing we can do is This is actually patently stupid, to be honest. So we have a small struct that just has a deadline, a timer ID. I will get very soon to why, the user pointer and the callback. And we just store them in a vector, which is a linear structure. So we can do our schedule timer like this. We make room for the new entry, and then we do an insertion sort. Just move things backwards until we find the insertion point, and then we're done. This is doing a tremendous amount of work. A lot of data copying. We're saving a little bit of memory since we don't have the two prev and next pointers, but we're doing a lot more work, shoveling data around. Cancel timer became more difficult now because since the data is moving around in memory, we cannot cancel by having a pointer that refers to the timer entry that we want to get rid of. So for every timer we store a timer ID, and to cancel we just search for it, a linear search, and then erase the entry, which is also a linear job. So enter another tool, Perf. Perf comes with Linux distro. You may need to install it as a separate package. Perfstat presents statistics from a whole program run using counters from the hardware and the Linux kernel. A disadvantage of this is, of course, that now you're looking at the real system. So what other programs are running on the machine does affect the result. There are so many counters that you can look at from Perf. When searching for cache-related issues, I usually use these. So I'm looking at cycles and instructions, because those are a decent proxy for how busy the CPU is. If the CPU does a lot of work, it can do several instructions per cycle. If the CPU is spending a lot of time waiting for memory accesses, you have the exact opposite. You have several cycles per instruction. And then I'm looking at L1 loads and L1 load misses, which sort of gives an idea of how efficient we are in terms of hitting or missing the cache. And speculative execution, we'll get to that one. That is really interesting. And this is fast. This is blazingly fast. You have practically no overhead at all. So that is good. Then we can also use perf record, which does statistical recording while the program is running. So every now and then it does checkpoints and see what are the counters now. And this makes sense because if you have a performance hotspot, you're likely to hit that point often. A downside of that is that you have to interpret the results a little bit carefully. So, for example, you can find that you have a lot of cache misses on an instruction that doesn't touch memory because it just happened to be on that instruction when it looked at the counters. And then use the call graph. By default, you just see a flat view of which functions where you are. But if the program is non-trivial, you really need to know how did I get here, because it may be one path that is critical and another road to the same function is not critical. And this is fast also, very fast. Not quite as fast as perfstat, but it's fast. Let's try. And now I have to actually log into another machine because, as I said, getting measurements now are affected by what's happening on the machine, and this video conference system definitely wreaks havoc with all kinds of measurements. So let's try this one first. Okay, slightly faster than what we saw with Valgrind, I think. But oh, this was a linear array. Let's do the linked list just to. So 3.4 seconds compared to just over a minute for Valgrind. So it's a lot faster, but we get the same result. And we see that this linear array, it's doing a lot more work. Many 700, almost 8 billion instructions compared to 2.5, and many more memory loads. But it's still faster, a lot faster. That is interesting. So let's do a record. Now here's where things become pretty unimpressive. Perf tool report to show you what's happening is not quite as impressive as Cache-grind is, Cache-grind, but it does give you information. So we can look at where do we have this. Okay, vector arrays, mem move, schedule timer. Okay, we can see compare and jump after equal. So this is when searching for the deadline and then moving the data around. Yeah, so it makes sense that we have cache misses there. Yeah. Okay. And cancel timer. This is the find if. Yeah. So not quite as impressive, but we see definitely a lot of in mem move and vector arrays. Okay. So what can we make of? One thing I asked on Twitter this, what surprised you the most when you learned about CPU cache? And I think Miro Knape just nailed it. Doing more work can be faster than doing less. And this that I just showed you, this is doing so much more work, with so many more instructions, and a lot faster. This can be very counterintuitive. The reason here for this being so fast is one that everything is in one contiguous block of memory, and the CPU has a prefetcher. So when you start accessing memory with a fixed stride in terms of addresses, the CPU very soon goes, I know where you're going. I bet you're going to read this address too. So it starts loading it in advance. So when you get to actually wanted to do the read, it's already in there. So and then you don't get a cache miss. So that is what's happening here. But we also saw that we spent a lot of time doing these linear searches. So maybe we should try a binary search. Like I said, there is a lot of data here. So it's 10,000 elements. It's a lot. We can try a binary. So this is fairly easy. The store is already sorted in timeout order. So it's just a matter of how we search for it. So schedule time, we can use the lower bound function from the standard library. This does a binary search to find the insertion point, and then we do the insertion. This is a linear operation though, so maybe we're not gaining much. We'll see. And cancel timer the same. We search for an equal range. There can be several timers with the same deadline. So we search for an equal range, and then we search for the timer ID in this range. So this should be reasonably fast, and then we do a linear arrays after when we have found it, like so. So let's have a look at this one. This can be interesting. So let's look at the search. We have the structure. We have the vectors, our schedule timer function exactly like I showed you, cancel timer and everything. So let's this linear array thing first, just as a comparison, and then the binary search. Okay, so it's faster. Nearly about twice as fast, so this is good. We see, yeah, cycles obviously lower, instructions much lower, good. Loads a lot lower, good. Load miss is somewhat lower, but wait a minute. 103.5% cache misses. You may be excused for being a little bit surprised by this. I certainly was. What this is actually the Spectre vulnerability that was on the Ranger a couple of years ago. So what's happening is that the CPU does speculative execution. So when it comes to a conditional branch, and if the condition is not yet computed, it doesn't know which way to go. It will take a chance. It say, I think the result will be true, and it follows the true branch. And if what you do there is some kind of memory access, and that is a cache miss, it will evict something from the cache, and it will initiate the read from memory into the cache. But then it figures out that, no, my guess was wrong. Sorry, we shouldn't have taken the true branch. We should have taken the false branch. So it throws away the results. So the memory read doesn't count. It never landed. It doesn't count. But the cache miss does count. And therefore, you can get this really surprising result with over 100% cache miss. And have a look at the details of this one. See where we have cache misses, and it's still primarily on memmove. Schedule timer doesn't really say anything, doesn't provide any information. Bummer. Cancel timer, no information. Shoot first. No information. And that is a problem. We're not really helped by the tools. We have to go to our own reasoning here and try to figure out. We definitely see that we spend 98% of our CPU cycles doing mem moves. So that is a hint. So going back to here, we can see, yeah, the searches aren't visible. We're not getting information, but we see that reads are down, cache misses are still kind of high, but it doesn't really matter. And memmove totally dominates everything. So what we should do now is obviously to write a much faster memmove, or not. It's actually pretty darn fast. So the thing is, why do we do so much memmoves? And like I mentioned, failed branch predictions can lead to very confusing results, because you can still evict cache entries. So just be aware of that one. Triple try map. It's really super popular to hate on map these days, because it's node based, it's pointer chasing, it's everything we don't want in a cache efficient structure. But we don't get mem moves, and mem moves dominate, so maybe we should try it. So this is a super simple implementation. We have our timer data is really just our pointers, and we use a multimap because we can have several timeouts with the same deadline. And our timer identifier is just the iterator. So schedule timer just inserts, we return the iterator, and cancel timer just erases. So it's super simple. And shoot first, it's if it's empty, we return false. Otherwise, we take the first entry, shoots it, and return true, and then we can go on. So let's have a look. We have this app thing with basically trivial implementation. So let's see where we are compared to that one. What do you think about map? Good, bad? Let's see. Wow. Okay. So are the people who hate maps wrong? What is this? Actually, this is too little to give us any information to speak of. So let's make this one a little bit bigger, do more revolutions. So now we cannot compare the numbers really, but we see a fairly high amount of misses, cache misses and branch misses. Do we end up with this now if we Perf report says on load misses? Not okay, we see RB tree. So yeah, the stub map is implemented as a red-black tree. So it needs to do balancing operations. So we have a fair amount of misses there and misses there. What's the issue with scheduled timer then? Oh boy, we're in the standard library now. That is okay. We get some help from getting source information here. So mkey compare. We see that we load a memory with an offset of 20 hex with a value we have in ECX compare, and an unsigned greater or equal conditional branch. So yeah, okay. So this is when trying to find the timeout time, to find the entry to insert before. Okay, that makes sense. That is what we have. Not very much more to say about that actually. So it's faster. It's actually a lot faster. But a lot of cache misses when comparing keys and when rebalancing the tree. Well, one of the issues of rebalancing the tree is doing more work than we need to do, because it keeps a whole global sort order and everything, and we don't really need that. There was a question on the Slack here about vtune. I personally have not used it, but yeah, I should mention that some alternative tools. vtune by Intel is a popular tool. I don't have enough experience of it myself to be able to say how good or bad it is, but there is definitely one. And AMD has a tool called UProf, if I remember correctly. I think it's like micro profiling or something such. I have never used it at all, so I have no experience there. I was told about a Mac specific tool, but I have presentation brain and I don't remember it, sorry. I can probably post it later when I figure out what it is. But yeah, so what we see here is chasing pointers. That causes cache misses. That's just how things are. But it's still faster, isn't it? I mean, a lot faster. But let's have a look at the size of the data structure. I'm running it with an average of around 5,000 elements, up to 10,000 here. And if we look at these times, we see that yeah, for these number of elements, it's fast. But if we look at the low end, we see I'm not so sure. So I did some normalization compared to the linear search in a vector. So one is having the exact same performance as a linear search in the vector. Higher is slower and lower is faster. And we see that linear search in the vector rules up until 200 to 500 elements. After that, the binary search or the map wins. So now you have to think for yourself in the data structures you write. How much data do you have? Is it more than several hundred elements, or is it actually like 20, 30? So that is a factor to think about. But when you have a lot of elements, then yes, algorithmic complexity does matter, but you can still think about cache efficiency in that algorithm, in that level of complexity you choose. So that is one thing to think about. So with that said, can we get log n lookup without chasing pointers? Because that should be faster. It really should be. So enter one of my absolute favorite data structures, the heap, by which I don't mean the free store. It's a heap data structure. It looks like this. It's a tree. This is partially balanced, partially sorted, perfectly balanced tree, where every node is sorted the same as or after its parent. So, and there's no relation between siblings, so it's not a complete sort order. And there is at most one node that has only one child, and that child is the last node. So here's an example of a heap. And the way we do insertion in it is we create room for the new element, but then we look at the parent of that whole and see if it's sorted after the element we want to insert. We trickle it down, and we repeat this until we find the insertion point, and then we do our entry. So to insert 7 here, we create room. We see that 10 is greater than 7, so we move it down. 8 is still greater, so we move it down. 3 is not greater, so we do our insertion. So this is good. And to pop elements from it, we just remove the top element, we trickle up the lesser child, and then we move insert into the hole that was created. So here, remove 3, the lesser child is 5, so we move it up. The lesser child is 6, so we move it up. And the lesser child is 9, so we move it up. And then we take the last element, that is 10, and move it into the free spot. And now it could have been that 10 had actually been, the number there was actually less than 9, so we should then have trickled that value up. An interesting property of this is if we give each node an index, we start with 1 at the root and its children 2 and 3, and then their children, and so on. So we can see an interesting property that the index of a parent node is half the node's index. So for example, the index 5, the number with 10, its parent is 2, because 5 divided by 2 rounded down is 2. Which means that we can represent this data structure in a contiguous store, just array indexing, which means that we can arithmetically calculate where we want to go instead of having to wait for an address to get a pointer so that we can read where to go. And since the CPU does out of order computation, it can actually go somewhere before it knows whether it needs to or not. It's not quite the same thing as the prefetcher, but the CPU can do its thing and calculate the address, load it, so that when you know that you want to go there, it's already done. But the heap is not searchable. So how do we handle cancellation in this one in a fast way? We don't want to do a linear search. So one thing we can do is we can actually split the data structure. We can have a store of actions, which is the callback and user pointer. And we have the heap, which just contains the deadline and an index into the action storage, so that we can find which action belongs to which. This means that now we have only 8 bytes of data that we need to move around to maintain the heap structure. And the way we cancel is to set the callback to the null pointer. Now, the astute observer obviously realizes that this means that cancellation doesn't shrink the structure. which depending on the use case may or may not be a problem, but realize that this is now a log2 data structure. So even doubling the amount of elements just means one more level. So I would say it's often not a problem, but your usage may show different results. As it happens, the priority queue actually exists. The heap exists in the C++ library under the name priority queue. So we just use that one. The schedule timer now stores a callback and user pointer in the action table, and then we push onto the queue the deadline and the index. Shoot first becomes more advanced because the top element may be cancelled, so we need to pop elements as long as the action callback is null. And then we can do the desired work. So let's have a look at this one. Okay, so somewhat fewer instructions, somewhat fewer loads, half the number of load misses. That is good. And roughly twice as fast. Okay, that is impressive. So let's try to analyze this a little bit more. Where do we have misses? First, adjust heap, push heap. Okay, so this is comparisons and to move into place, we can look more carefully. Yeah, the move of data. Obviously, we get cache misses there. Same here, I presume. Yeah, we comparing the element where to go with things. Yes, shoot first itself. Okay, not very much information in that one, I think. Not a lot of value in this one, so kind of hard to tell. But now we're actually finding that we can see that the random number generator is beginning to be visible. So this is not bad. So a lot fewer everything and just about twice as fast. So this is of course good. And if we look again at the execution time, we see that for large data sets, it's a lot faster, a lot, since we're not doing the pointer chasing and we're not doing any rebalancing and such stuff. But again, looking at the relative times, the blue curve is where the heap performs relative to the linear search in an array, and we still see that you need more than 100 elements for this to matter. And we see that since the red line is flat, the red line is how the heap compares to the map, and it's consistently better than the map, and we see that we have the same algorithmic complexity since it's a flat line at roughly 0.8. So there are still cache misses in the adjust heap functions, and I cannot help but wonder, can we actually do better than this? So if we look at our heap here and we try to look at how the cache lines fit, if we have one color for each cache line, we can see how it gets divided. And as we move through the heap, we can see a problem that, except for the root few nodes, we get one new cache line for every generation. So this is not very efficient. So I couldn't help thinking, can we do better? Can we do something like this? So let's make a bunch of mini heaps where each mini heap fits in one cache line, and then we build a heap of mini heaps. It turns out that this data structure has, of course, been invented before. It's called a B-heap. I did not know that, but it feels good to know that it has a name, so therefore it is useful, probably. And if we go through here, we can see that now we get 3 generations for every cache line. This is good. This really should get a better result. But it comes at a cost, because the structure becomes now a little bit more tricky. We have our array for a mini heap, and I choose to just waste index 0 because, yeah, it consumes a little bit more memory. But then I just do bit masking to get to the information I want. And then we have the next mini heap and the next mini heap and the next mini heap. And this means our big heap of mini heaps has a crazy log8 fan out in terms of cache lines. So this should be good. But the logic becomes very complicated, to say the least. So we can just mask and see what is the offset into a mini heap of any arbitrary index into our array. Find if something is a base or where the base is. If we can ask if it is a block root, because this matters when traveling up towards the root of the entire tree. So if it's not a block root, then we just do a local divide by 2. And if it is a block root, then the parent is the log8 calculations, which is quite terrifying, to be honest. And the same for block leaf when going towards the bottom of the heap. So the logic will look like this. If it is a leaf, we do one thing. Otherwise, we do the simple thing, and same when going towards the parent towards the root. If it's not a block root, it's a trivial. Otherwise, it's much more involved. And this is all for naught if we don't make sure that our storage is aligned properly. So I wrote an align allocator where I give an alignment, in this case 64, since this happens to be the de facto standard of cache line sizes. And I'm using C++17, where we have an align val t and aligned operator new and delete. So this became fairly straightforward code. And let's have a look at this one. So the allocator, all this really terrible code. This is complex. And this is also me just being completely obsessed by this problem. It would have been perfectly adequate to not do all this. So let's compare the heap and the B-heap. Okay, it's slower. Bad. But this is 01. Let's have a look at 03. And the B-heap for comparison. It's slightly faster. Actually, they are more or less equal. But what's really interesting is this. The normal heap, 120 million L1 misses. This one has 84 million odd misses. And in this case, this actually matters because it's a timer structure. The system does something, schedules a timer, does something, schedules another timer, does something, fires a timer. And the fewer entries we evict, the more data is still in hot cache for the rest of the program. And by this, I will finish. So what I mean with cache friendly is small data. For small data sets, linear search in contiguous memory is the fastest, period. The question is just how small is small. Less than 100, I would say, go for linear search. Avoid pointer chasing. Keep your working data set small. Use as much of a cache entry as you can. If you have taken the penalty of reading something and evicting an entry from the cache, make use of it. And fewer evicted cache lines means more data in hot cache for the rest of the program. Mispredicted branches can evict cache entries. Spectre and measure, because it's really difficult otherwise. Some resources you may want to read, I'm not going to repeat them. And here is how you can contact me and where you can find the presentation and also the sources. Thank you. Sorry I filled the entire spot and only had time for one question, but feel free to use the Slack or so. Thank you very much.